Okay, good day. The topic are we gonna discuss today is pressure coefficient. So this is very important because if I will demonstrate on how should I put wind loading in ETABS, the only thing that it's just cumbersome is putting the pressure coefficients because this pressure coefficients is different if we have or if we consider different scenarios in dealing with the wind. Like for example, scenario in which the wind direction is normal to the ridge or the wind direction is parallel to the ridge. So therefore, there will be different pressure coefficients. So this is a topic that we should really understand. And after this lecture, you will have an assignment about putting pressure coefficient. So ETABS has an auto wind load feature, but it is up to us to put the pressure coefficient if we consider the envelope. Sorry, if we consider the what you call that, the procedure there, it's not extends from diaphragm, so the other procedure, because extends from the diaphragm is not really good in designing wind. It's much better that in ETABS we consider the other one. So I will show that in later videos, but first let's understand what is this pressure coefficient CP. So CP and CN, these are pressure coefficients. So we will focus mostly, and in this lecture we will have some examples. And after, like I said earlier, that after these examples you will also have your own assignment. So we will focus on the directional procedure for the MWFRS, which is emphasized on enclosed and partially enclosed buildings. So let's start. So pressure coefficient CP or CN, we can found it in the what you call that, in the formula for the design pressure. So the design pressure P is given in chapter 27.3.1 in ASCE for enclosed and partially enclosed buildings. So this is the formula, and the CP is what we call the external pressure coefficient. So similarly, for open buildings, we don't have any internal pressure. As you can see here, we have some internal pressure here, this one. So you can see this QI, GCPI is what we call the internal pressure. So in open buildings, there is no internal pressure. That is why there is no quantity minus internal pressure, no, or the what you call that, velocity pressure for internal pressure. That's the term. So in chapter 27.3.2, that is in open buildings with monoslope pitch or trophy roofs. So instead of external pressure coefficient, since there is no internal, so therefore there is no external, we ASCE call it as the net pressure coefficient. So we don't need to bother about the internal pressure. And also for the velocity pressure Q, the QH here is for the mean roof height. While for this enclosed and partially enclosed buildings, it's either uh, Z height or the mean roof height. So Z height is for the windward wall, and mean roof height is for both the windward and leeward roof and the leeward wall. So anyway, it's not about that. It's not about the velocity pressure Q, but it's about the pressure coefficients CP and CN. So we need to understand this because this is very important if we want to assign wind loads in ETABS. So this is one thing that we need to understand is where do we get the CP or CN. So ASCE 7-16 and NSCP 2015 are almost the same, and we can get it from their provisions. So for the code provisions under different figures. So we will discuss first the enclosed and partially enclosed. So for enclosed and partially enclosed, we have the flat roof, we had the gable roof, we had the hip roof, monosloop roof, and mansard roof. So as you can see, we have different roof types, but for the sake of this lecture, we will try to do the gable roof. So anyway, gable roof, as long as it is enclosed and partially enclosed, we will use Figure 27.3-1 of ASCE 7-16 or Figure 207B.4-1 of NSCP 2015. So before I will go here, because we will focus on this figure 27.3-1, I will show you other pressure coefficient, especially for the net pressure coefficient CN, or for the uh, open buildings. So by the way, if we have a partially open building, the fourth or the latest or the recent enclosure classification, we would consider it here in this enclosed and partially enclosed, because partially open building has internal pressure. As you can remember in the introduction to wind loading in the other videos, I will just put the link there for that video. We have there the GCPI, or the internal pressure coefficient for the partially open building, and that is plus and minus 0.18. The same with the enclosed. So for partially enclosed, it is plus and minus 0.55, while for open building, it is zero. So open buildings don't have internal pressure. Okay. So for dome roofs with circular base, we use figure 27.3-2. So it is 0.3-2. Earlier, it's 0.3-1. So this is for dome roofs with circular base. And for roofs that are arc roofs, or buildings with arc roofs. So by the way, these two buildings are for enclosed and partially enclosed dome roofs with circular base. So we don't have any provision about dome roofs that is open. I don't know, because I don't have anything about it. But anyway, let's not focus on that. So we have this also arch roofs, enclosed and partially enclosed, also use figure 27.3-3 or 207B.4-34, NSCP 2015. Again, these figures are for the directional procedure for the MWFRS. So I have lectured about directional procedure and envelope procedure, the difference about them. Just see the video about the MWFRS and the components and cladding. So next, we will go to the CN, or the net pressure coefficients, that is for the open buildings. So for the open buildings like this one, monoslope roof, used figure 27.3-4. And for the pitch-free roofs, like for this open covered court, this is a pitch-free roof, figure 27.3-5. And finally, for the open buildings with true free roof, so the true here is this one. So we have a true here. So we use figure 27.3-6. And for the 27.3-7 is it has a different figure for open buildings with wind parallel to ridge. So for enclosure classifications of partially enclosed and enclosed buildings, the wind parallel to ridge is in figure 27.3-1. So it's there. So I will try to show you. So this is what you mean by wind parallel to ridge. Okay. The wind is blowing parallel to the ridge. So this is the ridge. And if the wind is blowing normal to the ridge, this is what we call the wind normal to the ridge. So before I will go, let's try to, before we'll go to what you call that example, I will show you some, I will show you the figures. So this is the main focus of our topic today is this. The figure 27.3-1, it is the MWFRS for all heights. So this directional procedure is very good for all, what you call that, for all heights, and it is recommended for any structures in, if it is just enclosed and partially enclosed. So this is figure 27.3-1, and I have lectured about these different notations. So watch the video about the introduction to wind loads. There is the lecture there about these notations. And this is what I'm saying. So this is the CP that we gonna use. So we have, as you can see in Windward wall, for all values of length over B. So length over B is this one. So I have lectured about this one. Is zero point 0.8. So meaning, if we use it with QZ, that is the velocity pressure at Z height. So velocity pressure at Z height is varying. It is a varying pressure. It's not uniformly pressure, no, uniformly distributed pressure, or it is a varying pressure. So we use zero point 0.8. So zero point 0.8 means that it is a positive pressure. So windward meaning, as I will review it to you, windward is the side in which it is directly on the side in which the wind is facing. The wall is facing to the wind. So that means that it is really a positive pressure. So for others, for leeward wall and side walls, so side walls is just meaning the side. So I did not really bother to include this in my explanation, but you can see later what is side wall. So leeward wall is the side in which it is opposite of the windward. This is for wall pressure coefficient only. So later I will discuss the roof. So we'll discuss first the wall pressure. So as you can see, for values of L over B, we have difference 0 to 1, it's negative zero point 0.5. As you can see here, as the length over B is increasing, the ratio of L over B is increasing, the CP is decreasing. And leeward wall, which means this is negative, it means that this is what we call suction. So mostly, in wind loading, most of the structure is under suction. It means that the elements of the structure is blowing away against the or blowing out or blowing away from the building. So that is why if the wind is blowing, most of the elements, the MWFRS is blowing away. So for side walls, the same with the windward wall, it's negative zero point 0.7. So it don't bother about this negative zero point 0.7 and zero point 0.8 because it is fixed for all values. So what if my L over B is not within this range from, let's say, 1.9 or 1.8? So just interpolate it. Meaning, if my value is 1.5, you just interpolate it, meaning that the value of 1.5 L over B ratio is between negative zero point 0.5 and negative zero point 0.3. So if my value is 3, then it's between zero point 0.3 and zero point 0.2. So it's very important, class, to know the interpolation. So if the value is not here, it is important to interpolate. So use them with, as you can see here, QH, QH, QH. So like I said, only the windward wall uses the varying load QZ. So next, we will go to the roof pressure coefficient. So by the way, in wall pressure, there is no such thing as parallel to ridge and normal to ridge. But if there is a scenario about that, you just flip the side wall and windward wall and leeward wall. Anyway, it doesn't bother. It's not important anymore in wall pressure. But in roof pressure, we have two what you call that, two tables. So the first table is for the normal to the ridge, and that is our theta, or our angle, is greater than 10 degrees, meaning our roof is not flat. Our roof is has slope or pitch. So theta is 10 degrees. This is what we will use in normal to the ridge. And for all angles, if it is flat roof or if it is monoslope, gable, etc., we will use this one, this CP here. So anyway, for normal ridge, if it is flat roof, theta is less than 10 degrees, you will use this and do not use this. So for flat roofs, use this for both ridge and parallel. So I think if you really want to have small load cases, just consider flat roof. But for the sake of it, it's much better to have higher degrees, or like say gable roof. Y class? Because in according to some research or according to some surveys, uh, especially in US, in hurricane prone zone like Miami or Florida, like that, they say that roofs with angles higher than 20 degrees or roofs with 25 degrees angle means that it's much more resilient against typhoon, against high winds of hurricane. So do not mostly use flat roofs, guys. So anyway, it's just something that I've read online, but let's try to discuss this roof pressure CP. So we use this one with QH, and this is mean roof height. This is fixed. Okay. So as you can see here, the parameters we use here is the mean roof height over the L. So I have discussed what is this mean roof height over the L. Okay. So uh, for less than 0.25, we have this. So if again, if our H over L is not seen here, we should need to interpolate. Linear interpolation is permitted for values of etc. So as you can see here, we have zero value. It is for use for interpolation purposes only. So, like for example, if our H over L is zero point 0.4, do not use zero point 0.5. Interpolate it. So it is between these two. It is between these two because zero point 0.4 is between 0.25 and zero point 0.5. Therefore, their values of different angle is also in between. Like for example, if it is zero point 0.4, the first scenario, like I said, no. So we have two scenarios, load cases. So scenarios is parallel to the roof at saka normal to the ridge, parallel to the ridge and normal to the ridge. So the load cases I mean is for the windward. So this is the windward roof. So for the windward roof, we have two. We have the first, if it is less than 0.25, we have suction. So consider the part that the windward is in suction or the windward roof is in suction, that is negative zero point 0.3 if our H over L is less than or equal to 0.25. And the other case is for the windward roof that is positive pressure at that is zero point 0.2. So similarly, if our H over L is zero point 0.5, luckily if our angle is 20 degrees, we don't have we only have one load case for this, and that is negative zero point 0.4. So 0, it means only zero point 0.4 for the windward. And as you can see, class, as the H over L is increasing, as it approaches to greater than 1 or equal to 1, both scenarios is we consider first angle 20 or 20 degrees angle because this is the no this is just I want to to discuss. So anyway, we have different angles and we have different, and we only focus on windward. As you can see here, guys, sir, we have two values for that is both negative. Why not consider only negative zero point 0.7? So do not consider negative zero point 0.7 because we have internal pressures. So uh, that is why wind load is bothersome to include in loading, but it is very important, class, that we consider this both. Although negative zero point 0.7 is greater, there is a chance that in positive internal pressure, because this is an enclosed or an partially enclosed, it has positive and negative internal pressures. The negative zero point 0.18 here will yield much more depending on that load case. So that is why you consider both of them. Do not just consider that it's just zero point 0.7 because it's higher. Also consider the negative zero point 0.8. So in greater than 1.0 or anything that we have seen here as double negative. So we have two load cases, that is negative zero point 0.7, negative zero point 0.18. Like I said, consider also the negative zero point 0.18. Yes. So as you can see here, plus and minus sign signify pressures acting toward and away from the surface respectively. It means that if it's positive, it's positive pressure. If it's negative, it's what we call the suction. So this is what I'm talking about, number 3. Where two values of CP are listed, this indicates that the windward roof slope is subjected to either positive or negative pressures and shall be designed for both. So interpolation is important. So practice to do interpolation, guys. So sir, what if my angle is not part of here? Again, do the interpolation. Do not be lazy, class. Do the interpolation. If your angle is between 20 and 25, and it is like said 21 or 22.5, do the interpolation. So 22.5 means it's between negative zero point 0.3 and negative zero point 0.2. And after that, interpolate also the if it is between 0.25 and zero point 0.5. So we have don't be lazy. Just do interpolation about them. Do not assume that it is 20 again. But like I'm saying, class, as you can see, we have a pattern here. The more the angle is becoming smaller and smaller, like comparing 20 degrees to 15 degrees, the coefficient of pressure is greater. You see, the coefficient of pressure is greater. But I don't want you to just saying we have 18 degrees roof. I will just use 15 degrees. No, just do interpolation. So I don't need to discuss any more windward roof for the normal to the ridge direction. Then leeward roof is much easier. So if the value is not here, do interpolation. Luckily for angles greater than 20 degrees, it's negative zero point 0.6. So if you don't want to have interpolation here, just give your roof greater than 20 degrees. So if you can read in news or in internet, roofs that have higher angle is much better in typhoon. So that is from the experience of other people. So that is one of the rules of thumb that we consider. We must try that our roof is greater than 20 degrees, or I think 30 degrees, but to be sure, let's try 25 degrees. So anyway, let's go to this. So another scenario is the wind that is parallel to the ridge, that is blowing to the ridge. If we have the front view, the wind is blowing in the front elevation of the building. So as you can see here, we have different. So obviously, on the windward side, our CP is much higher, zero point 0.9, negative zero point 0.9. So as it goes farther and farther away to the windward edge with these four levels of or along the length of the roof, the CP is decreasing. So for greater than 1.0, we have this one, and this B means that we can do reduction factor. This is the area of your roof. So anyway, what is this I'm talking about normal to the ridge? So let's try what I'm talking about. This is when parallel to the ridge. So this is what I'm talking about. This is what I'm talking about parallel to the ridge for all theta. So as you can see here, guys, if our wind is parallel to the ridge, as you can see here, this is parallel to the ridge. This is our windward edge. So our windward edge is the side in which it is in the wind, in the side of the wind. So assuming H over L greater than zero point 0.5, as you can see here. Uh, as you can see, our CP is big or is larger compared to CP at the end. So for both sides of roof, we don't have any more. We still have a windward edge for the roof. That is, this is the windward edge and this is the leeward edge. But for these two sections, it's the same 0.9, 0.9. As it goes farther away from the windward edge, our CP is decreasing. That is the meaning of horizontal edge. Okay. That is the meaning of horizontal distance from windward edge. And as you can see here, we also have two different values, that is negative zero point 0.9 and negative 0.18. So don't bother about interpolating about this negative zero point 0.18 because it's 0.18 regardless of your H over L. So by the way, class, our L here has shifted because it is parallel to the ridge. So our earlier, if it is normal to the ridge, it's different if assuming B and L is different, ha. So anyway, I will have some pictures about that for you. So For this negative zero point 0.9, negative zero point 0.9, we have different. So like I said, again, if we have different values, like they say it's not, let's say zero point 0.7 or zero point 0.6 or zero point 0.8, uh, interpolate it. But the interpolation here is between 0 to h over 2 at saka 0 to h over 2. That is negative zero point 0.9 and negative 1.3. And it's between anything and negative zero point 0.7 if it is greater than h over 2. So anyway, it's very easy to understand this table. Just do it, just do interpolation, don't be lazy, because it's very important that we get the correct CP. It does not really mean that we need to get the exact number of CP, but it's much better that we get the correct one, because it will really affect your wind loading in different scenarios. And by the way, since we have an auto loading in ETABS for the wind load, it's just important to know the CP, because it's the coefficient of pressure that we are just gonna input along with the load patterns of wind loading, the different factors like gas effect factor, directional factor, etc. But it's not the topic we are going to discuss today. So we are discussing about CP, the pressure coefficient or the external pressure coefficient in the case of enclosed and partially enclosed building. So let's go to an example. So we have this one. So this is wind parallel to the ridge and the wind normal to ridge. So as you can see here, we have a H, or the mean roof height. That is just the mean between the eave and the ridge. That is 23. Then our theta, or the horizontal angle, the angle between the slope of the roof and the horizontal length. So that is 20 degrees. So then for wind normal to the ridge, this is what I am saying, class. The B and L is different. So if it is normal to the ridge, the B is always what we call the perpendicular to the direction of the wind. So this is the wind, this is our B. As you can see the figure here. And L is just parallel to the wind. So L is 23. So L is 23, B is 36. We have H over L equals to 1, 23 divided 23 is 1, etc. So what if for the parallel to the ridge? So B, our B now becomes the 23 and our L becomes the 36. So it's both different class. So don't be lazy. Do these two scenarios: wind parallel to the ridge and wind normal to the ridge. So I will not bother, no. So I will go back here. For wind normal to the ridge, luckily we have LB that is less than 0.1, that is negative zero point 0.5. So it's easy. We don't need to interpolate, guys. So our LB is 0.64. As you can see, our LB is 0.64. That is less than 1. So automatically, we have negative zero point 0.5 for our leeward wall. So windward wall is 0.8. Side wall is negative zero point 0.7. For H over L, luckily, we don't need to bother about interpolating. So we consider greater than or equal to 1.0, and that is uh, 1. So this is H over L1. And our angle is 20 degrees. And 20 degrees, we also don't need to do interpolation for the normal to the ridge. And that is negative zero point 0.7 and negative 0.18. So since negative zero point 0.7 and negative 0.18, we do two load cases. And also, guys, so our answer for, okay, before I will go to the answer, before I will bother about the answer, I will discuss first this scenario A. So as you can see, in wind direction normal to the ridge, we have two scenarios, scenario A1 and scenario A2. That is left to right and right to left. We really need to consider this, but if in your judgment, guys, that this scenario is the same, just consider one. Because in anyhow, left to right or right to left, if it is for you, it is the same, then don't bother about doing these two scenarios, because you will have four. You will have four load cases, and in each case you have at least two positive and minus internal pressure. That becomes eight load cases for the wind normal to ridge only. So we have eight load cases. That is very much. So if we consider only one, then the load cases we have is four, because we have two scenarios, that is negative zero point 0.7 and negative 0.18 for the windward roof, and we don't need to change our windward, leeward, sidewall, etc. for coefficients. Only the windward roof, negative zero point 0.7 and negative zero point 0.18, as you can see here. And why it becomes 4? Because since we have two cases, we have also two cases for each. We have two cases each for internal pressure, that is positive GCPI and negative GCPI. So anyway, this is the answer. Okay, as you can see the answer here, we have this one, negative zero point 0.7, negative zero point 0.18 with the negative zero point 0.7 first load case is has a negative zero point 0.7 windward roof coefficient and a positive internal pressure. The second load case is the negative zero point 0.18 with also positive internal pressure. The third load case for this wind normal to ridge is a negative zero point 0.7 with negative internal pressure, and lastly negative zero point 0.18 with negative internal pressure, sorry. So our wall is the same for all. Our side walls is negative zero point 0.7, negative zero point 0.7, that is side walls. As you can see here, for all side walls, negative zero point 0.7. For windward wall, that is zero point 0.8. Windward wall is zero point 0.8 because the wind is, we consider the wind here. So even if you interchange the wind, if you change the wind to left to right, it's still just like a mirror image. So wind normal to ridge, either right to left or left to right, it will yield the same load for load cases, just mirrored. But anyway, let's continue. So let's discuss this again for the parallel. So we have finished the the normal, the wind direction normal to the ridge. So as you can see here, instead of doing this thing, we have distributed loading. Why not? Since if we want to consider both sides or both scenarios, bottom to top and top to bottom, why not just use negative zero point 0.9 or negative zero point 3 or negative zero point 0.5? But it's up to you what you want to consider. But for me, in my judgment, if for my judgment or for different cases that you need, instead of bothering to include this all, why not just try, for me, negative zero point 0.9. So 0.18, don't bother about negative zero point 0.18 because it's the same for all. So this is what I'm saying. Negative zero point 0.18 is the same for all. Just bother about negative zero point 0.9, zero point 0.5, negative zero point 0.3, 1.3, zero point 0.7. But anyway, like I said, I can transform it into this one only. So instead of doing this, what do you call that, with different regions in the roof, just negative zero point 0.9 or negative zero point 0.18. But if you really want a thorough analysis of your structure, it's much recommended that you do this, part, this part with different CP, depending on the length, on how the wind or the distance, horizontal distance away from the windward edge. Because as you can see, as the distance is going farther and farther away from the windward side, the coefficient of pressure is decreasing. So zero point 0.9, zero point 0.9, zero point 0.5, and zero point 0.3. Assuming that our H over L is zero point 0.5. So again, if we don't have the value for H over L here, do the thing about interpolation. Don't be lazy, class. Just do it. Just do interpolation. So this is what I'm saying. It is still based on your judgments of what you want to use. For me, I want to use negative zero point 0.9. Or for others, it's negative zero point 0.5, or for others, negative zero point 0.3, but it's up to you what you want to use. Or maybe you want to do this, it's up to you. So anyway, we have different judgment and different, what you call that. So it's really important to discuss these cases and these scenarios, because we don't know where would be our wind will come. But if it is in your judgment that the wind will not come behind me because there is a big obstruction, then don't do it. So anyway, it's up to you guys. This is just the general, or this is just some of my lecture about this. So this is how we interpret the horizontal distance from the windward edge. So horizontal distance from windward edge. This is how we interpret it. So anyway, let's go to the answer. So anyway, this is the answer, class. So as you can see here, unfortunately, we need to interpolate. So our H over L is 0.64, and we can't find 0.64. It's between zero point 0.5 and 1.0. We need to interpolate. So my interpolation yields for the roof pressure coefficients negative 1.012. Is this right? Sorry, no. H over L. Sorry, I'm looking about this one. So just look here. Just look here. Okay. Uh, Yan. So since it's 0.64, it's between zero point 0.5 and 1.0. So that means that it's between negative zero point 0.9 and negative 1.3. So our value for 0 to h over 2 is between negative zero point 0.9 and negative 1.3. So if you want to have a different, want to interpolate the greater than h over 2, let's say this one, and this one, we have the, call that, negative zero point 0.5 and between negative zero point 0.7, then negative zero point 0.9 and negative zero point 0.7. So anyway, that's it, no? So the answer I yield is negative 1.012. Negative 1.012. And the other scenario is negative zero point 0.18. So as I have discussed earlier, in the normal to the ridge, the parallel to the ridge also has four load cases. Because we consider the negative 1.012 and we consider the negative zero point 0.18. See? So you can see this is, we just need to discuss this. So therefore, in our two scenarios, we have 8 load cases. But as you can see, guys, if we go back here, as you can see, we really don't need to say that since this is negative zero point 0.6, this is negative zero point 0.7, we just consider the negative 1.012 because it's much higher. No, just try to input all load cases as much as you can, because the ETABS is the one who will generate the analysis or generate the shear and moment diagram. Just include all the load cases. So I will discuss it to you for you. So I will try to do demonstration on ETABS on how we will input this one with different examples. So let's go back here. And finally, this is my interpolation. So don't bother anymore about this. I know you know how to interpolate. And this is for the scenario B. So this is how I get negative 0.386 for the leeward wall. This is how I get negative 1.12 for the, what you call that, the roof for the parallel to ridge. So negative 0.386. So for windward and for side walls, so when we consider the parallel, it just flip, the wall flips. So our side walls now is negative zero point 0.7 here. Earlier our side walls is here, this side, and this side is our side walls. Now our side walls is negative 0.7 here now at saka here now. And our windward, since our wind is coming from the top to bottom, our windward wall is zero point 0.8. So okay. Then sorry, I have wrong here. Yeah, this is wrong. No? So sorry, this is wrong because this is between negative zero point 0.9 and zero point 0.7 and negative zero point 0.7 because this is greater than zero point 0.7. You can see here, we'll choose. As you can see here, this one, it's between negative zero point 0.9 and negative zero point 0.7. Why? Because negative zero point 0.9 here is h over 2. So that is greater than h over 2. Do not compare this negative zero point 0.9 and negative 1.3 because this is h over 2. So anyway, it's up to you. But although it's still h over 2, then it's up to you guys. But that's the interpolation there. So anyway, this is also correct if it is from here only, here na side. No? So anyway, so automatic. So transforms with the windward edge. So that like I'm saying, just use only one because you can also model it in etabs. You can model it like this one if you want to bother or not. But I will try this one because if I flip this one, if I flip this wind, if I flip this, or let's say this one is from the bottom to top, I will say top to bottom. The windward edge is also negative 1.012 here. So it's just like a mirror image. So I'm just using negative 1.012. And the other scenario obviously is negative 0.18. Do not bother about negative 0.18 like I said because it's negative 0.18. But it is important to consider both negative 1.12 and negative 0.18. Negative 1.012 saka and negative 0.18. So that is very very important class. And like I said, so let's go. And I think this is it. This is the last one. So this is your assignment. So try to do this class and instead of putting GCPI, just put plus and minus 0.50y inside. So we can know that the internal pressure coefficient is 0.55. So anyway, that's the thing. So this is the given. You can do screenshot here or just wait for the virtual learning environment. I will put this assignment and you can do this. And we will have a quiz in the meeting, in our meeting. So thank you, and I think this is it.